Thank you all for coming, and it is my pleasure to introduce Diego Ongaro, who has a long list of accomplishments. And I got to know him. I worked next to him in a CS lab for about a year at Stanford. I was an undergrad, and he was a PhD student. He was a year younger than I was, and so I had to call him Dr. Ongaro, and he called me undergrad. So that should give you an idea of how esteemed he is. He worked on RAM Cloud with John Ousterhout. He worked on, he invented Raft, and he's been working on LogCabin lately. And he is doing contracting work with Scale Unlimited, which is right there.
Scale Computing.
Sorry, Scale Computing. Those guys are right there.
They're limited.
Yeah, you guys are unlimited and awesome. And he told me the joke that he's probably not going to tell all of you, but when everyone sat down, he said, "Now there's quorum." So with that, let's let him begin.
I was not making a joke. All right, so this is my PhD work at Stanford University with my co-author, John Ousterhout, our advisor. I get to take all the credit, but he did half the work, so maybe thank him sometime. Anyway, so the motivation for consensus. Let's say we have some state we want to share. We want access to it across the network, so like a shared hash table. And you'll see why later. I'll call that a state machine. So we can put it on a single server and attach that server to the network. And that's good because it's easy. And it's also, you get really nice consistency properties where if you write something to the hash table, the next time someone does a read from it, they'll see what you just wrote. On the other hand, if it's just one machine, it's prone to failure. Whether that's a VM or a physical piece of hardware, things fail. That's just a fact of life. And so using Raft, we can kind of get the best of both worlds. We can keep that consistency, make it appear like we're talking to a single server, but actually have a cluster providing this service and get fault tolerance that way. Whether it's easy or not is kind of, well, you be the judge. Okay, so a little more formally, consensus is agreement on shared state, or sometimes people call it a single system image. And we want it to recover from failures autonomously. If we didn't care about failures, using a single machine is totally fine. So the property that Raft is going to give you is that if a minority of your cluster fails, that's not a problem. It'll maintain consistency, and it'll still be up and fully operational. So in our little 5-server cluster here, we can lose 2 servers, and everything's fine. If we were to lose a 3rd server, that's when the service would go offline. So it's going to prefer consistency and lose availability in that case. Once you get 3 servers back up, you're back online. So this little building block is the key to building a lot of storage systems from small to large scale. And that's why it's so important in distributed systems. Consensus is almost always used in the what's called the replicated state machine approach. It's kind of a bad name, but I didn't come up with it. So in this approach, here we've got 3 servers and a bunch of clients, and I'm showing the little hash table over on each server. So each server's got the state machine, which is the hash table, and clients don't interact with that directly. They submit their requests, and those requests get placed into a replicated log. So each server's got a copy of the log, which is supposed to contain the same sequence of requests. And the hash table, or the state machine, just replays commands out of that log in order. So if you have the same series of commands in all of the logs, then the state machines will end up in the same resulting states. And they'll also generate responses that you can send back to clients. Okay, so then all we need to worry about with the state machine is that it's deterministic. That way, you can't really use random numbers or depend on the current time in there. So that when the state machine on every server applies to the log, you do end up in the same state. The hard part is getting this replicated log to be the same on all the servers. And that's really the job of the consensus algorithm, and that's what I'll talk about today. As I said, we want the system to make progress as long as any majority of servers are up. And just to be clear, the failure model I'm talking about is servers can fail, messages can be dropped, and can be delayed. And then if a server fails, it can come back up later. But servers can't lie to each other. So assuming no memory corruption, assuming no malicious actors here. All right, so this is the building block called replicated state machines. And then how's that used in practice? Oftentimes, if you're building a large-scale storage system or really any distributed system at all, you need some configuration information, some cluster metadata, like which of the servers in the cluster, what state is assigned to each of them, that kind of thing. And so you can use a single replicated state machine to store that particular state. And then either every server in your cluster can directly query that replicated state machine, or you might have some more active server designated as the one that pushes information outwards. In the second approach, if this leader were to fail, then another standby could safely take over and become leader using kind of atomic operations that the replicated state machine would provide. So the other approach is, well, what if I want to store terabytes of data, petabytes of data? I guess terabytes is not impressive anymore. Well, if I just have a single cluster of machines, that won't be able to do it for me. So people actually partition their state or shard their state across many replicated state machines. And this is what you see with Google's Spanner project, Megastore, Hydrabase out of Facebook, which is based on Raft, where each replicated state machine is just in charge of managing one partition in the database. And then if you need to do operations across the replicated state machines in an atomic way, you might use two-phase commit. So how do we build a replicated state machine, or how do we build a consensus part? Well, when I started this work, the consensus was that you use Paxos. It was pretty much synonymous with the word consensus. And this is an older protocol from 1989, created by Leslie Lamport, who was last year's Turing Award winner. Unfortunately, he came at this from a theoretical perspective. He was actually trying to prove that it couldn't be done. He failed that proof and inverted it into a protocol. So it's like the most general thing you could possibly come up with is what he did. And that makes it pretty hard to understand. So here, NSDI is one of the top conferences, academic conferences in distributed systems. And one of our paper rejections, here's the quote we got: the dirty little secret of the NSDI community is that at most 5 people really truly understand every part of Paxos, with a little wink at the end, as in like, don't quote me on this one. By the way, I'm anonymous already. But that's bad, right? This is a fundamental protocol in distributed systems, or at least consensus is a fundamental problem. And we should be teaching this to, probably every OS class and every distributed systems class. Alex?
2 of those people died. Does anyone still understand Paxos?
Well, this is, so this is a special case of immutable state where, well, maybe it'll degrade over time. I don't know. But 5 is, I've met more than 5, but it's hard. And then it leaves you hanging. If you're trying to build a real system, as we were, there are significant gaps between the description of the Paxos algorithm and the needs of a real-world system, and the final system will be based on an unproven protocol. As in, even if you've got a proof of the core Paxos algorithm, by the time you extend and optimize it and end up with a real-world deployable system, you're nowhere close. And this is from Google's Chubby authors. That's a proprietary replicated state machine that they had inside Google. So, all right, that set the stage. I struggled with Raft for a while. I would go into John's office. I would tell him, "Nah, this is easy. Don't worry. Like we'll figure this out. Like by next week, it's great." And finally, he pushed me to try something different. And really, he started Raft. But the goal here is we wanted an algorithm that was really meant for systems building. Paxos is fine for theory, but if you're building a real system, you want that understandability and that completeness. You don't want to leave people hanging, and it should be pretty easy to teach or to learn. So our goals, yes, it had to be correct, complete, it had to perform well. These are things that Paxos already has. So if you want to displace it, you need all these things. But really, we were pushing on understandability. And so at every step of the way, we asked what would be easier to understand or to explain. If we had a design choice between two alternatives, we would ask this question. And I think that's a really important thing to keep in mind if you're attacking any complex problem. It's not, it's not always what's the most performant algorithm or what's the fewest lines of code. It's someone's going to have to maintain it, or some new person's going to have to learn it. And by asking this question over and over, it actually led us to an algorithm that we think is significantly better. So the problem decomposition is fundamentally different from the way Paxos approached it. The state space that it operates in is simpler, and overall it has very little mechanism to get the same job done. As academics, if we claimed understandability, we had to actually show it quantitatively, preferably. So we taught two classrooms, Paxos and Raft. We did this using video lectures that you can find on YouTube if you just search Raft User Study. So we taught a class at Berkeley, taught a class at Stanford, and we quizzed them afterwards to see, well, which one did they actually learn better? It might be a little hard to see here, but every line above the diagonal is a student that scored higher on Raft, and so that's 33 of the 43 of them. And then we also asked them in a survey at the end which one of these would be easier to implement on the left side or explain to a fellow student on the right side. And those blue bars for the people that said Raft. So I can talk for hours about this study. It's a lot of work, and I can try to show you or convince you that there's, I guess I can't show, but I can try to convince you that there's no bias in it. But I think it's better, since I have the time, to just teach you Raft right here, and then you'll kind of decide for yourself whether it's understandable enough for you. So, 3 parts. The first part is leader election. So the cluster will try to select one server to act as leader. The second, and then if that leader fails, because we want it to be fault tolerant, we want to detect the crash and elect a new leader. The second part is really normal operation, or log replication is what happens, where the leader takes commands from clients and appends them to its local log. And then it just tries to take its log and replicate that out to the other servers called followers. And so it'll overwrite any inconsistencies it finds on the followers during that stage. And the third section, titled safety, kind of ties these things together. So we can't have just any server becoming leader, if it's going to blindly overwrite the other logs, we need to select only a server with an up-to-date log to become leader. So each of these you can kind of think about separately. So that's what I mean by the problem decomposition. Now I'll switch to the fun part of the talk. So wake up. So this is Raft Scope. It's a half-assed JavaScript implementation of Raft. Keep your eye out on server 2, who's about to time out and start an election. And it's now leader, and it sent out a round of heartbeats. We're paused now, so I can speak. So that was quick, and I'll go through it more slowly. But you saw it was kind of one round of request-response RPCs to get that leader elected. And then the first thing it does is send out heartbeats so that other servers don't think that it's failed. Server 2 is our leader in term 2. So terms are the way that Raft divides time up. Once we've lost our leader for term 2, we'll be seeking a leader in term 3. So let me kill off server 2. And now server 3 is going to time out next. The circumference thing is the timeout. Great, so it timed out, and it says, well, I haven't heard a heartbeat from server 2 in a while because it failed, or probably because it failed. It can't know that. And so it's trying to become leader in term 3. So the first thing it did was increment its own term to 3. So it's got the 3 in the middle, and it turned pink. And then you'll note the other servers, they're still on term 2 because they haven't, there's what's called an asynchronous distributed system, so it's realistic in that time is not synchronized. These timeouts are actually randomized, so they're unlikely to happen at the same time. But each of these messages that server 3 sent out, they include the sender's term number. So every message in Raft includes the sender's term number. And the recipient will just take, if that's newer than the recipient's term number, it'll take it. So we'll see all these servers go up to term 3 once they process the messages. So server 3 has entered the candidate state. That's what you do when you start a new election. You campaign to become leader yourself. And to become leader, you need votes from a majority of the cluster in that term. So it's going to need 3 votes in this cluster. These little dots are representing the votes with a miniaturized view of the cluster. So you can see server 3 already voted for itself. When you start an election, you just vote for yourself. And it sent out, these are called request vote RPCs to, as the name would suggest, to ask for votes. Great. So those servers all updated to term 3, and the plus sign in the response means, yes, I voted for you. Those votes are grayed out right now on server 3 because it does not yet know that it's gotten the votes. But once it knows it has 3 of them, it'll become leader. And as I said, the first job as leader is to send out heartbeats. All right, any questions here? Yep.
He's voting for himself, right? So he needs only 2 votes from other cluster apart from.
Yes, he needs 3 total, but 2 remote ones.
Sorry. What happens if 3 crashes while it's campaigning?
In that case, probably what will happen is no one will become leader for that term. And I should have said you can only grant your vote once per term. Right now, first come, first served. So all the votes would probably be tied up in that term if the candidate crashed. Another timeout would then, in the next term, we'd probably elect a leader. you'll kind of see that here with the split votes. So Brian's question, what happens if two servers time out at exactly the same time? That's what's about to happen with server 1 and server 5. So they become candidates in the next term, which is 4. They vote for themselves. They request votes from everyone else. If it just so happens, because of the first come, first served rule, that server 4 votes for server 5 and server 3 votes for server 1, then they're each going to end up with just 2 votes, not enough to become leader. And so in Raft, well, they're trying to get server 2's vote. That's not going to work because I killed it. So what do we do? Well, this is one of those design points where initially we thought, well, okay, so not all hope is lost. There's only like these servers are up. They could talk to each other. They could work this out between themselves. Like, no, screw that. What we actually do in Raft is the stupidest thing is just wait for another timeout. And so in this case, server 3 will time out next, and it'll become leader in term 5. And so maybe we wasted 100 milliseconds or a couple hundred milliseconds, but it's pretty simple. Okay, and so if split votes happened all the time, you could argue that'd be too expensive. And so that's why all of the timeouts are randomized. So every time you hear a heartbeat from a leader, or every time you grant your vote, these timeouts have been resetting between the halfway point and all the way around the circle. Something random each time. And that encourages that only one server will time out first, and it'll have enough time to go and request votes before the others even time out. And I have a graph on this later on how well it works, which is pretty good if you tune it right.
Do you add a random amount to your timeout, or do you jump to a random timeout?
You jump to a random one. Yeah. So it is technically possible for, like, if server 4 got a heartbeat here, it could actually reduce its timeout. Who cares? It's fine. So that's it for leader election, unless there are more questions.
Question: how many nodes you need for operating cluster? How plus +1? For example, if there is 7 nodes,
Yeah, so
need
it's
4 nodes.
a strict majority. So you need a.
So other nodes never forget about server 2.
Yeah, well, so these at least in the visualization, they keep trying with server 2 until told otherwise. And so if
But implementation can emit servers.
Yep. You might want to do that on a longer time scale. So it's relatively cheap to change leadership in Raft. Evicting a server is cheap, but bringing up a new server where you might have to transmit a lot of state to it could take longer. Yes.
Yeah, so you might get to this later, but why do the new leaders need to send out heartbeats? What are they looking for?
So they are well, it serves a number of purposes, but for a leader election, they're just preventing other servers from timing out, which would, if I didn't say a key thing in here, which is if I'm the leader for term 4 and everyone else has moved on to term 5, my request will no longer have any effect. And so if I'm the term 4 leader, I really need to prevent others from timing out and incrementing their terms. And once someone's moved on to term 5, that's going to propagate virally, and I'm out of luck. Once we get past leader election, we're in log replication, which is where you'd expect a cluster to be like 99.9% of the time. So This whole thing on the right is showing the logs across the whole cluster. And here I have a 5-server cluster where server 1 is leader. And I have, after it got elected, I killed off servers 3, 4, and 5 so that they're out of the way for now. And I'm not showing clients in here, but let's say a client came up to server 1 and it said, hey, please, I have this command for the state machine. I'd like you to persist this into the log and replicate it. Say that happened 3 times. And so server 1 has 3 log entries in its log. And it writes its term number into every log entry that it creates. And I'm showing that instead of the command. So log entry 1 has term 2, log entry 2 has term 2, and log entry 3 has term 2. Cool. I'm going to let server 1 replicate 1 entry, and then I'll explain the rest of the stuff. All right, so now server 2 has a copy of that first log entry. So what's the dot and the arrow? The arrow is called next index. So this is the position in the log, and these are all local variables on the leader, but I'm displaying them throughout. So this is where the leader plans to send the next log entry to server 2. It's actually in flight already. It looks like that would be entry 2. And then the dot's actually used for counting up majorities. So the match index is the leader knows that it and the server agree up to that point in the log. So here the server 1's already gotten that acknowledgement, and it knows server 1 and 2 agree on log index 1, and that's it. So we can watch these both advance as time goes on. Great. Once the leader reaches the end of the log with a particular follower, it's going to send the same RPCs. These are called append entries, RPCs. But since it has no more entries, they're empty. And that's what I mean by heartbeat. An empty append entries RPC is a heartbeat in Raft. Okay, so at this point, I killed off 3 of the servers, and so our leader's only able to replicate to 1 of them. And you'll notice that all of the entries have dashed lines around them, indicating that they're not yet committed. So none of these commands have been acknowledged to clients yet because they're not safe yet. I told you at the start of the talk that we want the system up if any majority of the servers are up. Well, what if these 2 went down and those 3 came up? They'd have to run, right? They'd have to provide service, and yet they don't even have a copy of these log entries. So we're going to need to replicate to at least to a majority before we can call something committed. So let me bring a 3rd server up. Replicates that first entry to it. And now you'll see the match index for server 3 has advanced. So the leader knows that it and 2 other servers agree at least up through the first entry. And the commitment rule in Raft is that a leader can mark an entry that it creates committed, so an entry from the current term committed, once that entry reaches the majority of the cluster. And if you look carefully, you'll notice that server 1 has marked that first entry committed in its own log. So at this point, the leader can go and reply to that client, and it can say, hey, your entry is safe. No matter what happens now, I can start, stop, drop any messages whatsoever. That entry will make it eventually to all the servers. Of course, the leader needs to continue replicating the rest of the entries to a majority of the cluster, but it also needs to tell server 2 and server 3 that this first entry is committed now. that's important just so that servers 2 and 3 can keep their state machines relatively up to date. So it's done on the next RPC to them. It's just piggybacked with the append entries request. And well, you'll see it work here. All right. And on the next heartbeat, that's where that commit information gets across. Cool, done. So here we're at, I guess what you'd call a steady state, given that servers 4 and 5 are down, where all of the current entries in the cluster have been committed and acknowledged to clients. All of the state machines have processed up through index 3 as well. And now you can get a sense for how normal operation in Raft is, where a client would come and basically append an entry onto the leader. The leader would then do one round of RPCs to replicate that entry to a majority of the cluster. Once a majority of the cluster has acknowledged an entry, the leader marks it committed and replies to the client. All right, questions here?
None of the other servers can reply even on completed values. Is it write 1 3 many or whatever? Can you read?
So
Is it legal to read from others or from S2 or S3?
Some implementations do allow it, like Zookeeper, which does not implement Raft, but it's similar, would allow us read from other replicas. The problem with that is, unless you do a lot of work, those could be stale. So because the leader's the first one to find out about commitment, the other servers don't find out for another like half round trip later. If you do a read from the replicas, it might be behind. And that may or may not be worth it to you. It depends on the application. Jay Bennett.
Does commitment require persistence?
The leader does have to count how many replicas have acknowledged an entry.
I mean, when each entry, when you mark something committed, it has to be already persisted to some.
Yes, I should say the vote information and the log entries themselves all have to be written to disk before they're acknowledged. The match index, next index, and commit index are all volatile. So if you lose your commit index, for example, the next leader will just replicate a no-op and figure things out. So that's normal operation log replication. There's a couple of issues that can come up in log replication when you're dealing with leader changes or servers that have been offline for a long time. So I'll talk about those now. It's the same cluster, but I fast forwarded and I did a bunch of stuff. I had a couple more clients go up to server 1 and make requests, and it failed before it could replicate those at all. And so that's just setting myself up for later in the talk. And then I brought up, so I killed server 1, but I brought up server 4, and these servers selected server 2 as the new leader. And that's where we stand. It just got elected. It's about to send out its first round of heartbeats. And so what I'm trying to illustrate here is that server 4 is missing entries. Right? It wasn't around during term 2, and so it doesn't have any of these entries that are very important because they're considered committed. So how does Raft deal with this case? Well, the match index for a new leader, since that's the important one used for safety, that's conservatively set down to 0. So our new leader assumes that it doesn't agree with any of the other servers at all on anything. And yet, more optimistically, the next index is set to just past the end of the log. How does that make sense? Well, there's a built-in check in the append entries RPC, which is if I'm pointing at, if I'm about to send you entry 4, or in this case, there's nothing there, I'll send the term number of the previous entry that I have in the log. So here server 2 is going to send a heartbeat that says, hey, at position 3 in the log, I've got a term 2 entry. And then the other servers, they will positively acknowledge that if they too have a term 2 entry, or they'll negatively acknowledge that if they don't. So we'll see that play out with servers 3 and server 4. Right, so server 3 checks, it says, hey, I too have a term 2 entry at position 3 in my log. Yeah, I'm with you on that. So it sends back an acknowledgement, and you'll see the match index advance all the way to 3 on that guy. Server 4, on the other hand, nah, it's got nothing there. And so it's going to reply no. And then for server 4, we'll see the next index decrement. So looking for a place where the logs diverge. In this case, we have to go all the way back to the empty log. And then we can start appending from there. Since these entries were already committed, it didn't take that additional round trip to tell server 4 that entry I just gave you was committed. So I fast forwarded a little bit where I've created a term 3 entry and had that fully replicated, and everyone knows that it's committed. And I brought back server 1. So now you can see the problem with server 1's log. It has these couple entries that were never acknowledged to clients, but they're kind of occupying the same position in the log as an entry that we do care about, the pink one. And so what we need is server 2 to basically overwrite the log on server 1. These entries we call them extraneous. They're not worth keeping around. If those clients cared about that, they would retry again with a new leader. What's going to happen here is that same consistency check that we had before. Well, we'll have one round of heartbeats to get the match index up to where it should be. And then the leader will send over the pink entry. And with it will be a check for index 3. So the message is basically, take this pink entry, if and only if, at position 3 in your log, you have a term 2 entry. So in this case, that works out. They don't have to back up any. And server 1's just going to truncate the end of its log. We don't want to end up with like 22232, and then append the new entry. On to the third component of Raft, which is safety. This is the same exact cluster where I killed the prior leader and started server 5. And you'll note that server 5 has an empty log, so it doesn't have any of those precious log entries that we must keep. Well, what if server 5 were to time out first? Becomes a candidate, starts an election. Okay, so everyone see that if it actually became a leader, this could be disastrous because it's gonna, other clients could come up to it and it could just overwrite every log in the system. So we don't want that. So in the safety component, Raft introduces a new check during elections. You'll see that none of these servers actually granted their votes. They're all replying with a minus sign there. And so server 5 cannot possibly, with that log, server 5 cannot get votes from a majority of the cluster. In this case, every other server will tell it, you know what, my log's better than yours, so I'm not voting for you. And in this case, what we'll have, we wasted term 4, but server 3 is about to time out. Since it didn't grant its vote, it also didn't reset its timer. And server 3 does become leader since it's, it can get votes because its log is perfectly adequate. So what is this voting rule exactly? Well, when I'm a candidate requesting votes, I'll send over 2 integers. The term number in the last entry of my log, so 4, 3, and 3, and then the length of my log, 5, 6, and 4 in this case. And so if, say this middle server requested the top server's vote, the top server would say no, because by virtue of having that 4 as its last log term, as we call it, the top server is going to assume that its log is more up to date than the middle's. And similarly, if the bottom server asks the middle server, well, of course the middle server will say no because its log is strictly longer than the bottom server's. So when you take that property in aggregate, it means a candidate can only be elected leader if its log is as up to date as the majority of the cluster's logs. And what that means is if it can get a majority of votes, it has all the committed entries in its log. It may not know which of those are committed, but as long as it just keeps pushing that log and replicating that log out to the other servers, we've kept all of the entries that we promised to clients that we would keep. That argument is easier to see in the paper, so if you've got time, you can look at that. But hopefully you kind of see the intuition.
For the purposes of these calculations, you also count even uncommitted entries?
Yeah, so it's anything you've got in your log without looking at the commit index. To review then, I first talked about leader election, where there's a heartbeat mechanism, a randomized timeout approach to detect crashes. The timeouts are randomized because we want to avoid these split votes. If we had too many split votes, then our elections would take too long. The majority voting guarantees that there's at most 1 leader per term, and and asking people for votes kind of spreads the term number around, so it neutralizes the old leader. In log replication, so the leader takes commands from clients and appends them to its local log. It just overwrites the logs on the other servers with whatever it's got, and there's a built-in consistency check that says that logs can't differ in some sort of crazy mishmash way. They're going to agree up to a point, and then the leader will sort of overwrite the tail end. How's that?
So when you do the if there is differences, does the leader that was incorrectly elected or was trying to incorrectly elect, does it wait longer? Does the timeout go to the maximum so it doesn't try to vote again for itself? So
when you start an election, your timeout gets reset, and then hopefully those timeouts are much bigger than your RTT. So hopefully someone else would become leader and send a heartbeat over in the meantime. So in the safety section, I said we introduced this restriction in when you can grant your vote so that only leaders with all committed entries in their logs can possibly be elected. And that avoids any mechanism of having to transmit log entries to a new leader, which really helps keep Raft compact. I glossed over this, but if a new leader if it has entries from a prior term, it's going to defer committing those until it can replicate one of its log entries out from the current term. And that's needed paired with the election restriction to make this all work safe and not lose your data. I worked on the proof for a long time without having that, and it just wasn't working. This randomized timeout thing is interesting, right? And I did an experiment. I had 5 servers, gigabit Ethernet. They were all identical, dedicated hardware, so trying to synchronize things as much as possible. And I set the timeouts to a fixed 150 milliseconds. So there, I hit split vote after split vote after split vote. This is a CDF chart, so if you're not used to reading this middle line is the median, and 80th percentile, 90th percentile, etc. So you can see this is over hundreds or thousands of runs, and I had no election finish within 10 seconds, which, that's bad, right? But that's no randomness. So that's worst case scenario. Randomness is pretty cheap, easy to obtain, so we can do a little bit. If you just do 1 millisecond of randomness, now your median election times are down to a second. And you can keep scaling that up, so a more conservative value might be this blue line here. Choose timeouts randomly from 150 to 300 milliseconds. And there you can see your average election doesn't take much longer than 150 milliseconds. And let's see, and there's one more kind of fun thing to point out on these graphs. These little steps you're seeing, like in this red line, those are the split vote percentages. So here, like 25% of the elections are finishing with no split votes, but the remaining 75% do have split votes, and so we have to wait for that extra timeout period before getting the leader. And so you can see in a properly tuned cluster, that's closer to 95%. And of the remaining 5%, 95% of those will actually succeed in one more term. So it converges pretty quickly. I did a bunch of analysis on this, and I think if you take your one-way network latency and multiply it by 10, that's a pretty good range of randomness to use. So like if I have 1 millisecond latency maybe across a terrible data center, then you probably want to use at least 10 milliseconds of randomness. If you're like running in some garbage collected language, you're going to have to go higher than that. So there's way too many Raft implementations out there to even keep track of anymore. I used to try to list these on the Raft website, and it's out of control, and people don't submit pull requests enough. But these are kind of the top ones that I know of. Shout out to etcd, we got some people in the room. Some of you probably heard of Console from HashiCorp. That's another popular Go implementation. I work on one called LogCabin. So, LogCabin. It's got this brand new logo, got a laser cut version of that, if you want to check that out. It's written in C++. There's a network service similar to etcd or Zookeeper, where it's a hierarchical key value store that you can access across the network. LogCabin actually slightly predates Raft. I started it thinking that we'd be using Paxos for it, and that's when I ran into all these problems with Paxos, and Raft was born. But it was really a research project until recently, and lately I've been working with Scale Computing, shout out. All right. Working with these guys to get LogCabin to be production ready, deleting a homegrown Paxos implementation that they had, and hopefully releasing it to customers in the next couple months. So towards that, working on the 1.0 release of LogCabin. Pretty much the only thing left right now. Well, it just got an IANA port assignment, so I think 52, 54 or something like that is now the official LogCabin port. So I need to update it for that, and then trying to get rolling upgrades in place, which is a little tricky. So, for example, if you want to change the state machine code, you can't have state machines on different servers running different code. Otherwise, they're going to diverge and you'll never get them back together. And so you really need like a special log entry that says, hey, all the state machines, once you process this entry, now move over to the new behavior. Things like that. And we are actively looking for new users. We do think this thing is stable and production ready, modular a couple weeks. And so it's open source. It'd be great to have more people looking at it.
Question.
Yeah.
From the viewpoint of using it, how is it different from, for example, Zookeeper or NCD?
Not too different. So I'm guessing this is going to be more of a practical decision. Like, for example, Scale, all their software is written in C++, so it's a little annoying for them to take a Go or Java dependency for something critical like this. But if you've got feature requests and they won't do it, maybe I'm more desperate. All right. So we started this work because consensus is widely regarded as difficult, and yet it's completely fundamental to distributed systems. We needed something to fill the gap here and solve this problem, and etcd and all of those did not exist at the time. And so we designed Raft specifically for understandability. Our goal is to make it easier to teach in classrooms. There's actually some class at Brown going on right now where 30 students are each implementing Raft as a class project. It's pretty awesome. We think it's a better foundation for building practical systems, in part because the core is easier to understand. Also because you need a bunch of other stuff in a real system, and I wrote a book on this, my 250-something page PhD dissertation, where I think we've got simpler cluster membership changes than anyone else. That's if you want to change the makeup of your cluster, so you had 5 servers, say you want to go up to 7, well, now you're changing the definition of majority. And so all of that counting we did fails unless you go through some extra work to make that safe. So that's what cluster membership change is about. Log compaction is this Raft log. It's great as a data structure when you're actively modifying the log and stuff, but if you were to let it grow forever, you'd run out of space and you'd never be able to restart your machine. It'd take too long. So occasionally, like LogCabin, for example, will take a snapshot periodically and then throw away a prefix of the log. And different approaches to that are described in my thesis. Clients are also really important, and this is surprisingly one of the bigger sources of bugs in the real world, is how do clients interact with the system safely? Especially people have a tendency to screw up read-only operations because they think, well, just read from the state machine, it's fine. Not really. You have to make sure your state machine's up to date first. There's a lot more evaluation that I'm probably way over time. I don't have time to get into, but you can ask me or see my dissertation. Thanks. With that, I'll take questions. If you don't get a chance here, the Raft Dev mailing list is pretty friendly. I asked my first question the other day, and some guy from MongoDB kicked in, so it's a good little community.
So we did an Ask HN for people who couldn't be here, and one of the questions was, do you have a favorite implementation of Raft?
Whoa.
By language.
By language? Oh, I don't know. I mean, it was fun when this thing started to try to read through every implementation that came up. And then there's hundreds of them now. I can't do that. A lot of the implementations have caught on to this idea that it's smart to separate the core of the Raft algorithm from all of the kind of system software, like the network calls and like writing to disk, that kind of stuff. If I were to rewrite LogCabin, I'd probably opt for that approach. Part of why people write all these implementations is everyone's got their little tweak that they want to do. But I mean, putting something down as a starting point is great for everyone. And that was part of the point of Raft too. It's, if we just wanted one implementation to exist, we probably would have just worked on one harder. But by making it easier to understand and learn and teach, we hope that many implementations can thrive. Yes, gray shirt back there.
What's the most interesting tweak that you've seen that you would consider implementing into your own implementation of Raft?
The appealing ones, I feel like I mostly addressed in my dissertation. But people have funny needs. One that's, I think, important that I have not implemented in LogCabin is leadership transfer. So if you have a preference as to who's the leader, maybe you want one in your primary data center or something like that, or if the leader is going down and you just want to avoid the election downtime, then it seems like it could be useful to actually have your old leader say to the next leader, hey, as long as your log's up to this point, go ahead and time out right now. That's one I haven't implemented. Seems pretty generally useful. Dark gray, yeah.
So what's the most subtle implementation bug you've seen?
I don't know. So we caught one the other day where I just wasn't cleaning up some threads. I was just orphaning some threads that were, so in LogCabin, the leader will start a new thread for each of the other servers, and that one thread will be in charge of communicating with that one server. So we were orphaning those, and I don't know if that's harmless or completely terrible, but that was one of the harder ones to track down recently. I can't really speak for the other implementations.
Sorry, you have a set of actions, don't quite cover everything, you need to add models in not everything to do it all, maybe it'll work out. Was that your first thought, or do you have other ones that you started?
No, we were, this one came up a week before the user study videos were going to go out, and that was all timed just so that we'd make a paper deadline. So we were freaking out. We came up with a bunch of different ideas and didn't like any of them. And this one's actually, it adds one if statement to the code. It adds some cognitive overhead to understanding why. But I think it actually, it makes some intuitive sense. Let me go through the example. I'll put the text up because I don't remember. Is that big enough? Well, not for the text, but okay. So this is a sequence where we could either branch down or up. In this case, we've got server 1 was the leader, got to replicate this yellow entry to server 2, but didn't reach a majority there, and so that one's not committed. Then server 5 became leader in term 3. It also did not get to replicate this entry anywhere, the blue one, and then it failed. Then server 1 became leader again, and now it's leader in term 4. And so it got a request in term 4, and then it actually, as the log replication will replicate in order, the first thing it'll do is replicate that yellow entry to reach a majority. So there's two things that could happen next, right? If the server stays as leader, then the pink entry is going to eventually reach a majority, and then everything's safe because at this point no one else can become leader, right? With the last log term of 3, I can't get votes from that server, or that server, so now that one's out of the running for leadership. But take this point, and what if server 1 were to crash? Then server 5 right now can become leader because its last log term is 3, which is greater than 1, 2, and 2. And so it can get up to 4 votes in this cluster. It could become leader, and then it can trash the yellow entries. So where's the screw up here? Well, the screw up is that this yellow entry is more up-to-date information than the blue entry, right? Even though it's got a term 2, it is sort of newer. And so we could introduce a whole new term number to track like the replicated term versus the created term and try to fix things that way. But if you just say that, well, at this point, because server 1's replicating an old entry, it's not going to mark that entry committed yet. It waits until it replicates one of its new entries to mark the whole log committed. Then you kind of sidestep the problem more easily, I think.